Here, exam question. How are TCP management is being created between the sender and the receiver, and why are they important? Take it quiet, please, guys. Just, come on, guys. Three-way handshake. So how does that operate? How does that work? So let's take an example. I'm sending from A to B. So to actually establish a connection, this means this is a connection-oriented rather than a connectionless. That's first. So I'm trying to establish a connection between A and B. How will that operate? Basically, A is trying to establish a connection. In other words, A is the client. Meanwhile, B in here is the server. Okay? So A is trying to send an actual request. So the first thing to do is the client host sends a TCP synchronization. Client host sends a TCP synchronization segment to the server. That synchronization will have a specific initial sequence number, but no data. So basically, it's just synchronizing the connection to establish that initialization between the client and the server. And usually it will be a synchronized flag with an actual sequence number inside. Okay? That's what the sequence number is. So that's the first thing. So now the server being notified by the client, I want to establish a connection. I want to access, for example, an HTTP protocol using whatever you want to download something. And you're uploading using an FTP, whatever that is. You need to establish that connection if you are using a TCP as a connection oriented. The server will reply to you by the server host receives the synchronization, replies with a synchronization acknowledgement. So whenever the server receives that synchronization, it will reply with a synchronization acknowledgement as a sequence. That will have a server allowing you to allocate a buffer in that stage and a specific server initialization sequence number. So that will reply, i.e. the server will reply with an acknowledgement to the synchronization. And it will put an actual initialization sequence number as well. At that stage, at the moment, if I stop, what's the issue? Now I wanted to connect, and now I receive my acknowledgement. If I stop at this stage, what's the issue? Why? A connection is established. I've sent a connection. He replied to me, I'm happy with your connection. Why do I need a third step? I'll explain the third step and you tell me why is it required. Third step is the client, after receiving that synchronization acknowledgement with his own, i.e. by the server sequence number, he will receive, the client will receive the synchronization and replies with an acknowledgement segment to that acknowledgement, which may contain data or not, depends. So he might reply again, saying that yes, I acknowledged receiving your sequence number. And that's it. He might send data, and he might not. That's an option. Can't be in other conditions. The question is, why is this required? Not just required, why is this essential? Why don't I just stop in the second step, just here? What do you think? Which one? That's acknowledgement for the synchronization, and that's acknowledgement for that, basically.
So it knows to prepare to receive it.
Why would I need this text?
So B knows to expect information.
What is it indicating? It's a very simple answer. So we are indicating to the server what?
It knows that it can also receive from B.
Is it confirmation too? The confirmation to the server that the acknowledgement has been received.
That's it, simply. You're just acknowledging, I've received your acknowledgement. That's it. You know why? Because if that did not arrive, how would the server know that this connection has been established? You tell me. That's a very basic, simple answer. That was last year. It's just, why would I need a three-way handshake? It's simply to confirm the final communication between the actual server and the actual client. This will apply to the termination as well. But did you understand that part? Why is it required? Because if this got lost, how would the server know that you've received your acknowledgement? That's it. By the way, this is bounded by sequence numbers. I'm putting sequence, but I'm not putting numbers here. I'm leaving that vague. We had sequence numbers within our sliding window. We are going to have something similar within selective repeat. In the actual internet, within TCP, this is more complicated. Why? Because this number goes up to 200, 300. So that number is an indication of that connection, because now this is a session that's opened. In some cases, two sessions can come into play. That's important as well. There might be a late delay of arrival of the submission. If it doesn't have the same sequence numbers, we'll ignore it. I don't want you to worry about that at the moment. Let's see if you can understand the principle, the main part. Is that three steps understood? Okay? Any questions? Okay. By the way, after that stage, the client can send data to us a destination, and that's it. If that now the client tried to terminate the connection, how would that happen? Okay? So now we look at the termination of the connection rather than establishing the connection. So closing connection is very similar to establishing it. The client, i.e. the end system, sends a TCP finish control, a segment to the server. So he's basically sending him a message saying that terminate the actual connection. So now I'm trying to terminate the connection. The client will first send a finish control message. You try to say, I want to finish that connection. What will the server do, logically, if he accepts it? You just acknowledge it. He'll send an acknowledgement saying that I acknowledge your closing. So in here, this is closed. Because he acknowledged the closing. Can I stop now? Can I stop? Yes, no, and why?
No.
No, why?
Because the server needs to know that whether he received acknowledgement or not.
So what would you do?
Send in the
When you close it from the both sides rather than the one side of it. Because both of you need to agree. So both of you will send that finishing part. The client sent the finish and he received the acknowledgement. He needs to know that again. I need to connect that, complete that connection. So in now, he'll send a finish part rather than just wait. So this part, he'll try to close it at this stage. So he's trying to close the connection from this side. And now he will need to receive what? An acknowledgement saying that yes, that connection is being closed. So let's explain step number one. Step number one, client end system sends a TCP finish control to the server. And that's a finish control being sent. An actual server will receive that and acknowledge receiving that request, and then he sends a finish from his side. So step number two, server receives a finish and replies with an acknowledgement to close a connection, and then sends a finish. Step number three, the client receives a finish and then replies with an acknowledgement. And it enters a time to wait and respond to the actual acknowledgement. And this stage, there is a timer. Until that acknowledgement arrives, this might time out, and then the actual server will reset that finish again because he wanted to terminate the connection from the side. Okay? So the server will receive an acknowledgement, and then the connection will be closed. 4 steps for our doing. So any questions? Is that clear? With a small modification, you can have simultaneous finishing. It's very simple. So now let's go to addressing. We already discussed addressing in details within your sockets, and we explained how can a socket have an address of an actual transport layer with the port and the IP address. So to make these things clear, port numbers identifies a particular service on host. Each port number identifies a particular service on host. The endpoint uniquely identified by the socket, i.e. the socket will be the combination of the IP address of that machine and the actual port number of the actual process. That will create sockets. Okay? We already explained that in your socket lecture. I'm going to explain it again. Connection is uniquely identified by the source and the destination sockets. And these are the source, this is the actual source IP address with the source port number, and the destination IP address with the destination port number. So this is how it actually addresses for both sockets in full details. Usually we say that the port number and actual address for the socket is globally known. Why? Why is the actual address for the socket for the server is globally known? Why is it not the client globally known? Why usually those are known? The port numbers, the well-known port numbers, why are they known? And the 8080, the 2021, Telnet, the actual SMTP. Why are these known? What do you think? Why do you need the port number to be known globally? So, yeah, well, what do you use it for? Very simple. To use the service itself without knowing the actual port number, it's like a yellow pages. For you to access a service, you need to know the port number of that process. And that process usually is known to every user. So if I would say, what is the actual process, the actual port number for your HTTP? Is that's 8080 or 800? That's what it is. What about, for example, file transfer protocol? 21 SMTP, is that SFTP? 21. Telnet is 22. 23. So again, each one of those actual processes will have a unique port number, and they are globally known for you to access that service. Whenever you create some sort of a well-known in the future application which has a process number, you deliver that number to as people to use for them to be able to access your application. So now the process, the port number, is reflected to the actual process of the application. Okay? It will be associated with an IP address, but that will be within your socket. Port number can support multiple connections, each with a different source, port, and IP address. Now we are discussing error detection and recovery. Okay? And I think we are all familiar with go backend, but I'm going to compare go backend with selective and selective keys. And that's very important, guys. I want you to understand it. Okay? To provide a reliable connection in TCP, we need to add sliding window protocol to recover from errors caused by 1. Out of sequence signals. 2. Missing signals. Duplicate signals. And usually there is a CRC check software over it for a bit error recovery. In sliding window protocol, I'm going to compare now how the first 3 errors occur at layer 2 and layer 4. Okay? So the both errors recovery strategies that we all know as go backend and selective read. Go backend. We already know go backend from our sliding window protocol from layer 2. We emphasize heavily how does the go backend operates. For simplicity, I'll just explain go backend. Go backend will only acknowledge frames that have been received in order. Or if there is an actual signal or frame which is out of order, it will discard it and negative acknowledge it. That was the basic idea of it, but I'll explain now in full details and I'll draw exactly on the board how that's called. The sender has a k-bit sequence in the packet header. The window, i.e. the size of the window, is up to n, whatever that n is, 1, 5, 6, 10. Consecutive unpacked packets is allowed. Let's look at this picture. We have 4 sets of colors, a green, which is indicating an already acknowledged packet. So when I say already acknowledged, that case, if you remember, already acknowledged means I'm sending a packet. Remember, I'm using go back n, not selective repeat. So the basic that we did in our sliding window protocol is identical to what I'm going to explain now. So if I'm saying that acknowledge, what does acknowledge means? Simply that A sending to B with go back end strategy, error recovery strategy. Okay, so that's the same, we send a packet. So if that been acknowledged, basically that will have a sequence number, give it any number you want, let's say 1, and that number will be acknowledged from the receiver side. So basically that's acknowledged, and we all know that. Yellow are the ones that have been sent but yet to be acknowledged, which we had them in some cases being sent with the sequence number. We said, for example, S equals 2, S equals 3, for example. S is the sequence number. These are sent but not being acknowledged. So that's what is yellow indicates. Blue are usable but not yet seen. What do I mean by usable but not yet seen? So what I'm indicating in this 3 colors or 4 colors, what are they? What are they indicating? So if I look at it now, it's basically indicating N, is indicating your window size. So in the beginning, the window size will indicate how many is being sent, and whenever they are acknowledged, you can pass it on. And you can see that the acknowledged one is out of your window size. So if, for example, this is not acknowledged, this cannot be sent because the window size was, for example, 10. Okay? So basically that's what it is. All acknowledged packets up to the including sequence number of n can be cumulative acknowledgements, i.e. you need to receive the actual packets in sequence for you to actually acknowledge it and accept that packets. I'll show you in full details how it operates, and we already know that. You may receive a duplicate acknowledgement because the receiver can acknowledge more than one packet in any acknowledgement. Remember we had cases where an acknowledgement is sent but got lost, but another one came afterwards, and that covers what? That covers the two together, okay? We just want to see exactly how the error recovery will operate. So let's have a look at the rollback in action. So simply that's what it is. I'm sending packets from the sender to the receiver, okay? For now, let's look at it in details. I've sent packet number 0, packet 1, packet 2, and packet 3. And I waited. What does that wait indicate? Why do I wait? Why do I stop sending before? What do you reckon? With the size. Cannot send more than 4 files, for example. So I received those 4 messages, and then I started replying. See, the green line is coming after, if that's indicating the time, so the green one is arriving like in the 5th or the 6th millisecond. I'm not speaking about a timer, I'm just sending packets and receiving them. You receive the acknowledgement. So, packet number 1, arrived, 0, arrived and been acknowledged. Is there any issue with this one? Fine. If that arrived, can I send another one now? Can I send another one? Why?
Because the first one has been acknowledged.
But why?
Because the window size.
The window size now allows you to send more because we set the window size down, for example, in this case, it's 4. But whenever we want to get acknowledged, put it this way. 4 of them is sent. 1, 2, 3, 4. Okay? These are the 4 files that have been sent, 4 packets. Whenever one of them is being acknowledged, that will move on and shift to this side. So imagine these are files to be sent. Whenever that has been acknowledged, this will be passed on like that. And then these, so therefore 4 is allowed to be sent, and so on. So the window size is indicating whenever there's a file acknowledged, now we can send more files. So first thing, send an acknowledgement, so that's packet number 0. He accepted it and he sent packet number 4. He's discarding it because we will come to it in a minute. He received packet number 2. And everything is fine. He received it and he sent an acknowledgement. Everything's normal. Number 3 is sent, got lost. Okay? Number 3, sorry, 2 is sent, got lost. Number 3 is sent, what happens? Why? How do we recover from it? So clearly now, 3 arrived, but the actual receiver did what? Discarded. Why?
Number 2 was lost.
And why? What happened now? even assume
They are not.
out of sequence. Someone said out of sequence. When it's out of sequence, in go back end, the receiver will reject everything out of sequence. That's go back end. That's it. Whenever an actual sequence number is out of sequence, the order of the packets, he discards. So if you see the action now from the receiver side, it's just discarding in what? It's sending acknowledgement number 1 that I've received 1 and everything before 1. If you remember the go back end. He's discarding 4, 5. What happens afterwards? If you receive that negative acknowledgement, we call it, if that being received, he will just say that I'm resending it because you receive a negative acknowledgement. If not, that packet, number 2, has a timer. And what do we call that? You have a timer in the actual each message of those. And this timer, for example, might be 6, 5, 4, 3 seconds, regardless. Whenever it times out, resends packet number 2 and everything afterwards. Because all of those are being discarded. Sorry, part of go back in. Is that clear? Again, that's identical to your sliding window protocol part. Hope you're confused though. Well, it should be clear. Any questions? Is it clear? Any questions? Because I'm going now to compare it to selective repeat. Selective repeat. The receiver individually acknowledges all correctly received packets. It buffers the packets as needed. So in other words, if there is a packet that's not being arriving within an acknowledgement of it, and you start receiving it out of order packets, you will not discard information. You'll just buffer the site. Okay? Sender only resends the packet for which acknowledgements are not received, i.e. bounded by the time. Sender window is in any consecutive sequence numbers, and again limits the sequence number of sent with unacknowledged packets. Let's see if the operation makes sense with that. So let's see the first part of the image, with the A side. So now I have the same colors. The green one is already acknowledged. Yellows are yet to be acknowledged. Green usable, i.e. the critical window size. Look at the other side, i.e. the actual image in the receiver side. The actual input is out of order, buffered, but already acknowledged. The gray one are expected, not yet received. The green one, acceptable within the order. Can anyone understand the principle underneath? Basically what that is. Same example. First packet arrives. Let's say he acknowledges it. Let's say acknowledge this. Sequence number 2 got lost. Number 3, let's say arrived. What happens next? So tell me, if he's now trying to acknowledge, what happens? For the first packet, what does he do? Does he accept or reject? First packet. Accept, arrived successfully, and he's trying to reply. So he replies with his acknowledgement for the first one. This one did not arrive. This arrived out of sequence. What will he do? In go back end, he discarded. And he say that I've received this and everything before that. In selective repeat, what will the receiver do? Instead, will he discard it or not? So what will he do exactly? He's creating this, for example, the same window size that you have that image in the below, that he have that set of files being have a place of it. Whenever he acknowledges a file, he just say acknowledged. And he indicates that's been acknowledged, and he moved the size of the window. He allows to receive more packets. If he received, for example, that's 1, that's 2, that's 3. He did not receive 2. He received 3 before that. i.e. the acknowledgements, what will he do? He will leave that empty, he'll buffer it, and he'll say that I acknowledge receiving 3, and that's it. So what he's done, he did not discard 2, he just leaving, he did not discard 3, he's waiting for 2 to arrive, whenever that arrives. He doesn't care. So the receiver will still buffer everything until he receives, so let's continue with the example. Let's say he received the 4th packet now. S equals 0, for example. Let's say, let's make it 4, so, and here we are with the selectivity, so make things easier. So that's 4. He received that. What will he do? He'll just say, I've received it, and he'll acknowledge it. And let's say this. You tell me. No. You tell me. So you say it doesn't matter. Whatever I'm acknowledging, what I'm creating. So again, my window size at the moment is n. Is that fine? If I acknowledged this one, did that affect the window size? So now you're allowed to send 10. Put it that way. So these are 10 files. Now let me make it easier. 1, 2, 3. Let's say you're allowed to send 3. So that's 1, 2, 3. Is that right? Until you receive the acknowledgement, can you send more? Before you receive that, can you send more than 3? Before you receive the acknowledgement. Yes or no? You can't. It's 3. Whenever you receive the acknowledgement at A1, now you're allowed to send more, regardless of this one. But that will create an issue for you. Now you say that I'm not receiving 2, I'm just receiving acknowledgement at 3. Do I shift my window size or do I wait? Because there's 1 now missing. I don't know when that will arrive. No, you don't, in that case. Now you start waiting until that one arrives. It might be like another, those files, for example. And the window size allows you to receive until that one. Whenever you receive that one now, the window size will shift. And now you are allowed to receive, okay? That will make sense in the next slide because I'm explaining that in details. Let's return to the basic part. Whenever there is a file goes missing, you don't discard it. You buffer the actual location, wait for the others to arrive. Until this arrives, then you move on. The window size will stop until you receive everything. And I'll show you in the next slide the operation, exactly. So this image I'll show the idea. Look at this. This is your window size. This is not moving. Those are arriving as you acknowledge this. Those pink ones. This one arrived, you acknowledge it. But your window size is still stuck here. In other words, you're only allowed to receive those blue ones now. When will that shift? Whenever it goes, in the beginning, this one arrives, and afterwards, this one, and so on. Okay? So if this arrived first, your window size will pass 3. Now you're allowed to receive another 3. That makes sense. Look at this one. That will make hopefully let's try it. Let's try this one, okay? The actual bracket is the window size. Look at the sender side, okay? Don't look at the receiver, just look at the sender at the moment. He sends packet number 0. Arrived successfully. What did he do? Look at the receiver side, he acknowledged it. He's moving that packet as well. So when he acknowledged it, whenever that received, look at this step. Look what happened to the window size. By the way, window size here, shifted 1. That allows you to send more. Look at the afterwards. Let's say you send packet number 1. Packet number 1 arrived. Again, shifted. By shifted means you're allowed now to send 4 again. Is that making sense? Okay. So let's try this, okay? First packet sent, i.e. packet 0, arrived to as a destination. The destination received it, and he acknowledged receiving it by sending his acknowledgement. Packet number 1 again, so that's 0, now 1. 0 and 1 has been sent now. 1 arrived successfully. Again, he's trying to acknowledge it. Packet number 2 is sent, but got lost. Nothing arrived to his destination, you don't know what happened. Now packet number 3 is sent. Now window is full, because the window size is 4. When the receiver will go back in, if you receive that out of sequence, usually he discards it. In this case, because it's a selective repeat, he'll buffer it. He'll store it, wait for it to arrive the other way. Okay, so he received it, sent it back. You can see that he's stored it now. He kept it on 2. He did not move it to 3. See that one? Kept it here. He's waiting for the packets to arrive. And now he's sending his acknowledgements. Now he sent the acknowledgements, packet size moved bigger. Within the 4th step, he's allowed to send the 4 because the window size is not full. And then he's allowed to send the 5 whenever he receives the acknowledgements. What happens to packet number 2? Whenever it times out, whenever that times out, you resend it, i.e. the sender. Whenever you receive it, look at what happens. When you receive that, now everything shifted, and now your window size is empty again. So now you have a receiver window size and a sender window size. You have it both sides as a window size with selective view. That's why I did not include that with the access sliding window protocol, because it will be hard to track compared to our part where discarding it is easier to control rather than this one, buffering it aside and then going back to it. Is it clear, guys? Okay. I have a comparison. I have some questions again. Now let me finish that slide. I'll leave that slide and then I'll do this. I'll stop it here. Okay, let's do this. Okay, let's try to focus on this one. Just 2 slides left, so people can wait. Selective repeat dilemma. Okay. Look at those 2. I'm actually trying to imagine that between the sender and the receiver, there's like a curtain, i.e., the sender cannot see exactly what's happening. I want to compare the 2 examples and see whether does it make a difference or not. Example is the sequence number are 4, i.e. 0, 1, 2, and 3. My window size is 3. I'm using selective repeats. Okay, to complicate it. Look at the first image. First one is sent. Arrived, he's trying to acknowledge, the acknowledgement got lost. Second one sent, third one sent, and so on. Those 3 has been received and acknowledged. The problem is the acknowledgement got lost. From the sender side, what will happen? No, tell me.
He's going to wait till the time out.
He waits some of the time, thank you. He waits some of the time out, and he will do what? Retransmit them. Is that right? So he waits because he did not receive acknowledgement. That means the receiver did not arrive, did not receive them. Is that right? He's now resending them. The first file he's sending is identical to the first one. Question is, would the actual receiver know this is a new or a duplicate? Because it's a duplicate. He's resending it. He doesn't know. The actual receiver doesn't know. Okay? The same example. Look at the second one. So let's stop and look at the second one. Same thing. First one sent. Arrived, acknowledged. Second one sent. Arrived, acknowledged. You see, until now the window size is 3. Nothing happened. Third one is sent, and that's he stopped. Window size is 4 because window size is 3. Now, if you can see that you received acknowledgement, whenever you start receiving the acknowledgement, the window size allows you to send more. So he's sending it 3, but 3 got lost. Okay? So he sent 0. Now 0, in this example, is it a new or is it an old one? It's a new one. It's a new packet being sent. For the receiver, is there a difference? Does he know? This is a new or old one? No, he doesn't know. The same problem within the first one. The question is, how can I solve this issue? What is the issue? The issue is, first of all, the issue is, if the receiver cannot know exactly whether I'm receiving a new file or whether I'm receiving a duplicate one, how can I know exactly the differences? What do you think? What should happen? What will control this? I'm saying as a hint, what is the relation between sequence number, size, and window size?
Can you not send acknowledgement as well as with the packet? Like what we were doing in Windows sliding protocol.
We are assuming it is a half duplex and the only acknowledgement is being sent. Okay? That's not the key.
We're using the three-way handshake.
And the three-way handshake is just indicating initialization of the connection. Nothing to do with it.
like make sure the sequence numbers are like double as high as window size?
Exactly. That's exactly what it is. Whenever the window size is less than the sequence number, you'll have that issue. With selective repeat, the issue is the window size must, and I say must, be larger than the sequence number. That's a key, guys. With selective repeat, the window size should be larger than the actual sequence numbers. So this issue will not happen. And I'll show you for 2 examples afterwards, but that's the key. I'm trying to make it one slide explaining the differences. Again, that's important, guys. What do you focus on this differences? Go back and selective repeat. The big issue. Basically, you can have up to n acknowledged packets in the top right. We know that's fine. Until you enter the actual timeout, then you stop receiving acknowledgement, or just times out. Similar to selective repeat. Those are similar. Sender can have up to n unacknowledged packets in the pipeline. You know that's identical to the first one. Receiver only sends what we call it accumulated acknowledgements, i.e. it doesn't acknowledge packets if there is a gap, i.e. out of order, discarded, or send a negative acknowledgement. Receiver sends individual acknowledgement instead for each packet. He waits, he buffers. Sender has a timer for all these unacknowledged packets. If a timer expires, we transmit all unacknowledged packets, all of acknowledged packets. Meanwhile, with the selective repeat, the sender maintains a timer for each unacknowledged packet, but when the timer expires, it only transmits the unacknowledged one. Basically, that's the list. That's the main difference between those two. Okay, I'm not going to continue. But I think I have 5 slides left, but that's fine. We'll get to the next lecture. Tutorial next week. I'm looking to that. But thank you for your time. If you have any questions, please.
Can you not send more than one acknowledgement? Isn't that in protocol? Like you can in this packet?
Yeah, that would be the key. I'm here trying to make it more clear. So if I increase the window size or decrease it, so if the window size is 3 rather than 5, would there be a problem? How can we solve it? I'll leave it to the next lecture to explain the details. Yeah. Going back to the question here, where you said. By the way, this is arriving afterwards. Don't be deceived that this is sent here. It's just arriving. It's not sent here and
let's say we lost that packet, yeah? And we send another as well.
Wait, that's selective repeat.
Yeah.
Receive those 2, lost that one.
That's on buffer.
Okay, that's been buffered. You
Yeah.
can see that he's now accepting, he's moving. Now he accepted, he moved. Now he buffered.
Yeah.
Because now 2 is not received. He's waiting for 2, 3, 4, or 5. Whenever he received that, then he shifted. He's accepting 4, and then he stops. 4 or 5, he stops. He cannot receive more. There are 4. Okay? So basically, what I'm trying to explain is, if that got lost, he not discard information, he would save it until he received that 2, and now back, look at this. He received it now, he received it now everything being already been stored, he just put 2 before them and he moved on. That's basically what it is.
That's good.
Okay?
Yeah. That's good. Thanks.